Now look at first problem. They provide 4, 2, 2, 1, 1. So total number of vertices are 5. Total number of vertices are 5. So total number of vertices are 5. Therefore, max degree of any vertex must be 4 only. Max degree of any vertex must be 4. That is the first property, right? Just observe the property. Max degree of any vertex. Max degree of any vertex must be n minus 1 only. Okay. Here total number of vertices are how many vertices we have? We have 5 vertices. 5 vertices. What is the maximum degree now? Maximum degree is equals to 4. Of course, it is satisfied. Okay. But by satisfying only that condition, I cannot see this simple graph. Remember that. Okay. In a simple graph, that property is hold, but if that property is holding, we cannot see the simple graph. Remember that. Okay. So I cannot eliminate first option. I cannot eliminate first one. Let me verify that first property for the remaining. Here 4 vertices are there. Maximum degree must be 3 only. Yes, maximum degree is 3. So that's the reason. Second one also we cannot eliminate. Third one also we cannot eliminate. Fourth one we cannot eliminate. Now interesting point, listen. Total how many vertices we have? 6 vertices. Total we have 6 vertices. 6 vertices. And in 6 vertices graph, maximum degree of any vertex must be 6 minus 1, that is 5. But what we have? 6. Therefore, it is not forming simple graph. It is not forming simple graph. Is it clear, everybody? By using this property, I eliminated that option. Maximum degree of any vertex is n minus 1 in a simple graph. In a simple graph, maximum degree of any vertex is n minus 1 only. But here I have total 6 vertices. How can I get a vertex of degree 6? Is it possible? No. Therefore, we can ignore it. Okay. Next. Here total we have 6. So therefore, there are 2 vertices of degree. Total we have 6 vertices and max degree is equals to 5. Yes, maybe it is valid. We'll discuss later. And here also maximum is 3. No problem. So by using first property, I can eliminate option 5. I can eliminate option 5. Is it clear? Examination point of view, finding right answer is not at all important every time. Eliminating wrong answer is also important. So here I eliminated option 5. Let me check second property. Sum of degrees of all vertices must be even number. Okay. Sum of degrees of all vertices must be even number. Let me sum up first one. 4 plus 2, 6, 6 plus 2, 8, 8 plus 1, 9, 9 plus 1, 10. So it is even number. It is even number. By satisfying that condition, I cannot set a simple graph because that property, sum degrees vertices theorem, is applicable for any type of graph, not only for simple graph. Okay. So here by verifying that property, I cannot say directly the simple graph. Okay. Let me hold this one. Okay. Right. Second property also satisfied here. Second property satisfied. Now look at second option. So 3 plus 3, 6, 6 plus 2, 8, 8 plus 1, 9. Yes, sum of degrees of all vertices are 9. But according to sum degrees theorem, sum of degrees of all vertices must be even number. Therefore, I can eliminate second option by using second property. Right? Let me check this one. It is sum of all degrees equal to 6, which is even number. Maybe it will form. I don't know. Okay. So next one is also even number. Next one. If you sum up all these, 6 problem. If you sum up all these, 5 plus 5, 10, 14, 17, 19, 20. So total value equals 20. 20 is even number, right? Maybe there is a possibility that it forms a simple graph. Okay. Next one. So it is 14. It is also even number. Sum of degrees of all these vertices are even number. So by using second property, I eliminated second option. Is it clear? By using second property, eliminated second option. Now look at third property. Third property. Number of odd degree vertices must be even. Number of odd degree vertices must be even. Number of odd degree vertices must be even. Let me check what are the odd degree vertices now. Please look at here. In first problem, it is odd degree because 1 is nothing but odd degree. Here also it is 1 odd degree. Total of how many odd degree vertices now? 2 odd degree vertices. 2 odd degree vertices means even number of odd degree vertices. Even number of odd degree vertices. Clear? Next one. Second one, anyway, it is eliminated. How many odd degree vertices are here? 6 odd degree vertices. 6 odd degree vertices. 6 odd degree vertices means obviously it is even number of odd degree vertices. Even number of odd degree vertices. Therefore, I cannot eliminate option 3. Next, here, all are even. We can no need to discuss that. Look at problem number 6. How many odd degree vertices are there? 1, 2, 3, 4. So there are 4. Even odd degree vertices are even. Therefore, it is okay. We can accept it. Okay, we can accept it. Next here, 6th, 7th, and also we can accept it. Therefore, by using third property, I cannot eliminate any option. Right? By using third property, I cannot eliminate any option. Right? We can eliminate. And maximum number of edges in a simple graph of n vertices must be n into n minus 1 by 2. Maximum only n into n minus 1 by 2. Clear? Then how can I verify this property? Look at first one. According to sum degrees vertices theorem, sum of degrees of all vertices must be equal to 2 times of edges, right? 2 times of edges. Therefore, so according to sum degrees vertices theorem, if I sum up all these values, 4 plus 2 plus 2 plus 1 plus 1, it must be equal to 2 times of number of edges. 2 times of number of edges. So 4 plus 2, 6 plus 2, 8 plus 2, 10. So number of edges must be equal to 5. Number of edges must be equal to 5. So because it is 8 plus 2, 10, 10 is equal to E. So E is equal to number of edges equal to 5. But in 5 vertices, maximum how many edges will exist? 5 vertices, maximum how many edges will exist? Maximum how many edges will exist? Vertices edges will exist? N into n minus 1 by 2. So 5 into 5 minus 1 by 2, right? Maximum 5 into 5 minus 1 by 2. So which is nothing but 5 into 5 minus 1 by 2 is nothing but 15 edges are there. So here we are having 5 edges. Therefore, we cannot eliminate this one. Cannot eliminate this one. Okay. Now let me check here. Total 6. 6. Therefore, 6 is equals to 2 times of E. So E is equals to 3, which is also valid because maximum number of edges are n into n minus 1 by 2. So n means here 6. 6 into 6 minus 1 by 2, which is exceeding 3. Therefore, it is correct. Means this is valid representation. I hope you are following what I'm saying. Maximum number of edges are only n into n minus 1 by 2. If it exceeds maximum number of edges, I can eliminate the option. Okay. Next, if you see this one, total, we are having 6 into 2, 12. So 12 is equals to 2 into number of edges. Sum of degrees of all vertices equals to 2 times of edges. The number of edges is equals to 6. Okay. Therefore, we cannot eliminate this option also. Okay. Next option. So 10, 14, 17, 19, 20. So we have 20 that equals to 2 times of number of edges. The number of edges is equals to 10. 10. Maximum how many edges are possible for 6 vertices graph? 6 into 6 minus 1 by 2, right? Which equal 15 edges. Of course, we have 10 edges. Therefore, no need to eliminate. Next this one, which equal to 3, 12, 14. 14 equal to 14 equals to 2 times of edges. 2 times of edges. Then what about number of edges? Number of edges is equal to 7. 7. The 5 vertices graph, in 5 vertices graph, we will have 15 edges maximum. So we have 7 edges. Means that fourth property, whatever property we discussed here, that what is the property number? Fourth property, right? Maximum number of edges. So none of the option exceeding max number of edges. None of the option exceeding max number of edges. Therefore, we cannot eliminate any option. Okay? In some cases, the moment if you see the given degree sequence, there is a possibility that total number of edges are exceeding max number of edges. Then we can easily say it is not a simple graph. Is it clear? Yes. So by using properties, we can easily eliminate the options. Okay. Now let me check remaining options whether they are forming simple graph or not. Okay. Now look at first one. I'm going to discuss plotting method now. So 4, 2, 2, 1, 1. Is it a simple graph or not? Is it simple graph or not? Okay. So I can take 5 vertices I can take 5 vertices. Okay, I can take 5 vertices. So otherwise, let me draw in a separate way because there is no space. 4, 2, 2, 1. First problem. 4, 2, 2, 1. I want to verify the sequence representing simple graph or not. 4, 2, 2, 1, 1. Okay, 4, 2, 2, 1, 1. So we want to discuss whether it is representing simple graph or not. So the plotting method says that you can take 5 vertices now because there are 5 vertices are there. We can take 5 vertices. Let me take 5 vertices. 5 vertices. And there is a vertex which is having degree 4. So I can say there is a vertex which is having degree 4. So clearly, this is a vertex which is having degree 4, right? This is a vertex having degree 4. Let me call it as something like A, B, C, D, E. So clearly, C is having degree 4. Next, there is a vertex degree 2, but no, none of the vertex having degree 2, right? Okay. Suppose if I make A as degree 2, okay. So this is a vertex. What is the vertex? That is C. Now I can say 2 means A is having 2. And whatever 2, B is also having 2. Remaining 2 are having degree 1. If any vertex having degree 1, that vertex is called pendant vertex. Pendant vertex. Okay. So clearly it is representing simple graph. Is it simple graph or not? Yes. This method is called plotting method. This method is called plotting method. Okay. Means we can draw the vertices and we can draw the simple graph. Okay. Then you may ask the question, sir, here I have only 5 vertices, therefore I can draw the graph. Suppose if I have more than 10 vertices, if I have more than 10 vertices, is it possible to draw the graph? Obviously, it will take time, right? In such case, we can take help of Havel-Acme research, which we'll discuss very shortly. Okay. Therefore, first one is representing graphical sequence. Second one, anyway, we eliminated by using properties. Third one, see, look at third one, whether it is representing simple graph or not. Third one is very simple, therefore I can draw it here only. I want 6 vertices, so I can take 6 vertices. Each vertex is having degree 1. Okay, so I can join like this. That's all. The simple graph with 6 vertices, 3 edges, and degree of each vertex is only 1. Therefore, it is a suitable simple graph for the given degree sequence. Therefore, third one is valid. First one is valid, third one is also valid. What about this one? Degree of every vertex is 2 in this case. Degree of every vertex is 2. And how many vertices we have? 6 vertices. Let me take 6 vertices. And degree of every vertex is 2. So I can draw like this. So clearly, degree of A, let it be A. Degree of A equal to 2. Now degree of B also 2. Degree of C is 2. Degree of D also 2. Now degree of E also 2. And degree of F also 2. So every vertex having degree 2. Right? In fact, it is cycle graph. Cycle graph. Maybe you are listening first time, you may get confusion how to draw quickly diagram like that. But by practicing problems, definitely you can easily draw the graph like this. Okay, it is nothing but a cycle graph. Cycle graph. Right? What is cycle graph? We'll discuss later. So fourth one is okay, and fifth one we already eliminated. What about sixth one? It's a very interesting problem. Okay, look at sixth one. There are 6 vertices. There are 6 vertices. Then one vertex having degree 5. What does it mean? One vertex having degree 5. What does it mean? It means it is connected to remaining all other 5 vertices. Is it correct or not? Yes, it is correct. Okay. Let me take this fourth problem, sixth problem once again. Problem number 6. Problem number 6. 5 5, 4, 3, 2, 1. We want to verify whether it is representing degree sequence of simple graph or not. If it is representing, then we can say the graphical sequence. Okay. See, suppose assume that it's a degree of V1. It is a degree of V1. It is a degree of V1. I'm taking it is V1, V2, V3, V4, V5, V6. Okay. There are 6 vertices are there. And first one is called degree of V1. Okay. Degree of V1. So let me write that point also. Degree of V1 is equal to 5 and the degree of V2, degree of V3. Here. So degree of V1 equal to how much? 5. What does it mean? That V1 is connected to remaining all other 5 vertices. Is it correct or not? V1 is connected to remaining all other 5 vertices. Okay. Suppose I'm taking V1, E1. We are having vertices V2, V3, V4, V5, and then V6. Total we have 6 vertices. Suppose if V1 is connected to remaining all other vertices, then only I can say degree of V1 is equals to 5. Similarly, degree of V2 also 5. Degree of V2 also 5 means V2 also connected to remaining all other vertices. So clearly V2 connected to V1, V2 connected to V1. Now V2 also connected to V3, V2 also connected to V4, V2 also connected to V5, V2 also connected to V6 like this. Correct? So that is the meaning of degree of V2 equal 5. Now please understand, if there are 2 vertices have of degree 5, 5, then definitely we cannot find a vertex V6 whose degree is 1. Whose degree is 1. Will you accept this sentence or not? Because 2 vertices are like V1 adjacent to remaining all other vertices, V2 also adjacent to remaining all other vertices. Then how can I find a vertex whose degree is 1? Because V6 already adjacent to means there is a commonality between 2 vertices. Then only those 2 vertices are called adjacent. So V1, just look at this. V6 is connected to V1, V6 also connected to V2. Then how can I say degree of V6 is equals to 1? Is it possible? No. Therefore, it is not a valid sequence. It is not a valid sequence. Here I can write one important property. You can remember that property. The property is, suppose let us consider there are n number of vertices. There are n number of vertices in the graph. N number of vertices in the graph. Then the following degree sequences, are not a valid graphical sequence. What is the meaning of graphical sequence? Means they do not form any simple graph. Not a valid graphical sequence. What are the invalid sequences? Now, see, look at this one. Let us consider that there are n vertices, n number of vertices. Then the following degree sequence are not valid graphical sequence. What are those sequences? First one, suppose we are talking about only degree sequence. Please remember degree sequence. Suppose one vertex having degree sequences degrees n minus 1. Another vertex also having degree n minus 1. It means that this vertex V1, suppose assume that it is V1. V1 having degree n minus 1, V2 also having degree n minus 1. Then definitely we cannot find a vertex whose degree is 1 or 0. Is it correct or not? Means let it be n minus 2. And so if I continue, maybe it is 2. I cannot find vertex whose degree is 1. It is not possible. You can ignore it. Because we already mentioned that there are 2 vertices having degree n minus 1. If 2 vertices are having degree n minus 1 means those 2 vertices are already adjacent to all other vertices. Then how can I get a vertex whose degree is 1? Therefore, it is not valid. It is not valid. Please understand clearly. Okay. Next, second sequence, second invalid sequence. Suppose it is n minus 1, n minus 1, n minus 2, up to so on. Suppose D. There is a vertex whose degree is 0. Is it possible? No. Because you already mentioned that V1 is adjacent to n minus 1 vertices. V2 also adjacent to n minus 1 vertices. Then how it is possible to get a vertex of degree 0? No. Therefore, it is also not valid. Not valid. Is it clear? Please understand these points. Suppose if it is n vertex graph, assume that we are talking about not valid sequence, right? If it's not valid, we can stop there. Suppose if I say it is n minus 1, n minus 1, n minus 1, up to so on, n minus 1, and then n minus 1. Means every vertex having degrees n minus 1. Is it possible? Yes, it is possible. If every vertex having degrees n minus 1, that graph is a simple graph with maximum number of edges. Is it correct or not? Okay. It means that it is looking like this. What is the degree of A? That equals to 3. Degree of B also 3. Degree of C also 3. Degree of D also 3. So here n is equals to number of vertices, 4 vertices. 4 vertices. And degree of every vertex is 3. Degree of any vertex here, that is 3, which is equals to 4 minus 1, which is equal to n minus 1. Okay. So which is valid sequence, right? So in fact, it is forming a simple graph with maximum number of edges. Therefore, it is a valid sequence. It is valid sequence. Okay. So please remember these key points. Here, only first two are invalid. First two are invalid. Please remember that. First two are invalid. Okay. Now, by using these properties, now come back to this question. Come back to this question. Sixth question. There are two vertices of degree 5. There are two vertices of degree 5. Then definitely I cannot expect a vertex whose degree is 1 in the 6 vertices graph. Right? Therefore, I can eliminate option 6. So option 6 eliminated. Right? And what about option 7? So total we are having 5 vertices. Total we are having 5 vertices. Of course, just now we have seen if we have n vertices, we can have every vertex at most n minus 1 edges, right? At most n minus 1 edges. Okay. Here almost all vertices are there. 4 vertices are having degree 3 and only one vertex having degree 2. Let me check, is it valid or not? Is it valid or not? Seventh question. Question number 7. There is a 5 vertex graph. In that 5 vertices graph, 4 vertices are having degree 3 and only one vertex having degree 2. Let me check, is it possible or not? Okay. Let me check, is it possible or not? Suppose assume that we have taken 5 vertices. 5 vertices. Okay. And each and every vertex having degree 3. So clearly this vertex having degree 3. This vertex having degree 3. And the second vertex also having degree 3. A is having degree 3. B is also having degree 3. And C also having degree 3. D is also having degree 3. Whereas E is having degree 2. Therefore, seventh one is valid. Okay. This is a way we can do the problem to verify whether the given sequence is forming simple graph or not.